Good morning, everyone. Welcome back to the last and final landslide seminar series. Today we are in session C. We have a lot of good presentation todays. Just to introduce myself, if you don't know who I am, Steve Sachs, assistant professor in the Department of Civil and Environmental Engineering at the Swanson School of Engineering. And kind of without further ado, we're up against the clock, kind of get everything in. So I will introduce our first speaker, who is Anthony Falbo from Fisher Associates. Who's going to give us a presentation today on an introduction to static LiDAR scanning. So Anthony, the floor is yours. You can go ahead and share your screen and get started.
All right, can everybody see that? The slide there? Well,
you're good. Oop, I can't see the slides yet, Anthony.
You can't?
I cannot. Yeah.
Okay. Let's see here. Yeah, it's showing on my screen here. Is there anything else I have to do other than hit the share screen on it?
Depending on what your options are and what you were trying to share, it doesn't look like I'm seeing it, whether it's your PowerPoint or your PDF. So maybe just try it one more time.
Okay.
Maybe choose whether you want to share the PowerPoint. If you go into share, then it'll give you options to either share your screen or the PowerPoint. You might be sharing the wrong screen. There we go. Now we're seeing it.
Okay.
Good to go,
Great.
Anthony.
Wonderful. Okay. Sorry for the delay there. Yes, and thanks for the introduction. Yeah, Anthony Falbo from Fisher Associates. I'm the regional survey director here for the tri-state area. So I'll skip ahead here. We're going to just be talking about kind of like a high-level view of the static LiDAR scanning. So as an overview of kind of what we're going to go over here, we'll go into real brief background of scanning, applications, strengths and weaknesses, and just go over a few examples of scanning. So first of all, the way it works, essentially it's kind of like radar. So it's the instrument, the LiDAR instrument is shooting these lasers out, and it can be anywhere from 1,000 to 2 million per second. These lasers are shooting out, they're hitting an object, and the instrument is keeping track of how long it takes to get back to the instrument, and that's how it can range the distance from the instrument. And it'll create a point for each object that it hits. And then when it's all put together, you've got a model of the subject area. So the major types of scanners are airborne and terrestrial. So the airborne ones, they're obviously off of a flying platform. Terrestrial can be mobile LiDAR, or also the static, which is what we're going to focus on. So for the mobile LiDAR, there's lots of different processes that have to take place for this to work properly. So you've got GPS that's going on, you've got the LiDAR process going on, you've got base station correction, you've got a moving object. So there's a lot of different processes going on to be able to collect the data and accurately depict it where it's supposed to be on the Earth. Similar process for the terrestrial mobile scanning, say for a vehicle or a boat, things of that nature. So there are a lot more going on with that. Now, when it comes to the static, essentially this is like survey equipment you might be familiar with. It sits on a tripod or it's mounted to a permanently fixed position, and it's performing the static scanning operation. It's shooting out the lasers. It's staying in one place though. Another thing about these scanners, they used to be very expensive. It was hard to process the data. It took a long time, but over the years, the price has come down. The technology has gotten better. The computers can process a lot more, and storage is less of an issue. So it's becoming a lot more viable. So some of the applications for this scanning would be land surveying, civil engineering, geological, ecological monitoring, city planning, architecture, archaeology, crime scene preservation, so forensics, video gaming. So there's quite a few uses for the technology. So in regard to land surveying and engineering, say, a very good use would be structure site monitoring. So retaining walls, if you want to see if there's any kind of shift or movement over time, pavement, bridges. It's very good for as-built surveys. Great if you're going to perform like an ALTA survey or existing conditions. You get all the information on the site, even more. And later, it's information you can draw out of the scan if needed. It's great for historical preservation for architectural purposes. It just does a great job of collecting all the information there. In regard to geological or ecological monitoring, so like say for mining, it's great for, monitoring, say an unlined tunnel to see if there's any shift or there's any, kind of movement or anything like that. Or monitoring the supports inside for deformation. Analyzing hard to reach rock structures that would be extremely difficult to get by hand and dangerous. Slope monitoring, which is obviously very important to what we're talking about here today. Leaf density, say like capturing existing stream bank conditions. It's a very important tool for that. So the beginning of all of it, if you don't have good control and you're trying to compare this data to other data, you're going to have a problem. So survey control is a very important component of this. Survey control is essentially a network of known points or positions, solid positions that we can get back to, know the coordinates, and we can tie data to it, like the scan. With the scanning, we can put this and, we can compare it to old data that's on an arbitrary coordinate system, or tie it to, newer information. We can put it on state plane. We can do whatever we want as long as we have good survey control. And the way we tie the scans together is we use kind of like loud sort of objects that can be set on these known positions, and then those can be correlated. We can tie the scans together based on where those like objects are within the scan. So like a general workflow with the scanning here is that, essentially we'll collect all the data in the field. It'll be a big, massive point cloud with all kinds of data all pushed together. We'll bring the information in, and then what's called classifying the point data. So we'll break it out into certain, items like bridge structures, pavement, people, vehicles, things of that nature. And you need to do that because it's hard to make changes and to make the proper corrections or adjustments, clean up weird scan data or noise in the scan if it's all together. So if we can classify it, we can break it into separate layers, and then we can freeze those layers and then focus on the important ones to us. Say if we're doing a monitoring of a hillside or something like that, you want to remove some of the other objects that you're not really interested in. So these are examples of scans that have been classified and broken into features. You can see like the lights are in the red, and that's a different layer. The building's all blue. The earth or pavement is all in the brown. So some examples of scans that we've worked on and how we've used them. Here's an example of a bridge that failed. It was this is in New York, and the bridge, it failed. It was a pedestrian bridge right over top of a roadway, and the DOT wanted to get as much information as quickly as possible so they could open the roadway again. So scanning was a great tool for this. We're able to scan the whole area for forensics, and then so that it could be used for analysis. And then they were able to remove the bridge, the failed bridge, so they could open the road up again. Another example is a pretty large helium tank that needed to be moved, and so it was spherical, and they wanted to know the geometry, the exact geometry of it, so that they could come up with a plan to move it so that when they went to shift it, it didn't kind of shift away from them and fall and kind of roll away. So we scanned the object. You'll notice there's a dark part on the top of the dome there. That is snow. So this was scanned in the winter, and as you can see, there's certain things that are not great for scanning. It will not give you a good review. You can't scan snow. You can't scan leaves. You can scan them, but you're not going to get what's underneath, obviously. So another example was there were some repairs to be done on this bridge that was joined a rock face. And to do this by hand would have been very dangerous, and would be very difficult to get the detail, the level of accuracy needed for design work for the base mapping for this. But this was scanned in a matter of minutes, basically assembled and then used for review and design. This is not one of our scans, but I thought it was a great example and pertained to what we're talking about here. You can see that this scan here was probably done in about 10 minutes, 15 minutes tops. And you can just see the level of detail that you can pull out of something like this. You get a great amount of detail. You could go in, you could measure this, all the say the posts in there, you could get the distances, and you could come back and obviously monitor it and see, compare the, if you create a surface from the first one to the second one, you can see what the shift is as well. So overall, the strengths of this scanning is assurance. The scan data is adjusted to survey control after the scans are registered. And to be honest with you, today, they've really stepped that up to where a lot of that happens in the field with the registration. It's safe. You can capture valuable data in areas where field crews you don't want to push them out. It's very risky, but you can even get better information than they could by hand, honestly. Such as like elevated platforms, confined spaces, busy roadways is a big one for that. That's thorough. There's generally no bad brake line shots or anything like that the field crew forgot to get. It's all in there, unless there's something obscuring it, obviously. That's superior to traditional surveying for volume surveys, for example, because it does, you're not gonna, it'll get all of the dips, the voids, the bulges, all that type of stuff. It's really hard to do by hand. You're just not gonna get all that stuff. And you have a very dense point cloud. So you're getting millions of points in there, and you just can't do that type of stuff by hand. This reduces second trips. So, costly remobilization, sending field crews back to the field to get information. You've got information there. If there's something that comes up later that says, oh, it would have been great to get, say, the wire heights, it's going to already be in the scan, and you could get that information. So some of the weaknesses are reflective surfaces. Doesn't work well with that. Snow, heavy rain, thick vegetation. You're not going to have a lot of success with that. So you really have to be thoughtful of how you use it. It's a tool, and it has specific places where it works best. So, and the thing to keep in mind with it, it's not a push button, magic silver bullet type thing. It's going to be more labor intensive in the office, but the time usually balances out because it's less time in the field, and obviously it's much safer, and you get more data with the scanning. So that's my brief overview, intro to static scanning. So if anybody has any questions, I'd be more than happy to field them as best possible.
Thanks, Anthony. Any questions for Anthony here today in terms of his presentation? Anthony, thanks. It's a great introduction, showing us kind of a little bit about the technology, giving us an idea in terms of what's going on. So
great.